Imagine you discover something that shouldn't exist. Not a new planet, not a hidden tomb, just a tiny extra in the mathematics of nature. A missing piece so small it first looks like a rounding error, until it forces physics to admit it was describing the atom with an incomplete language. In the early 1920s, quantum theory was finally starting to work. Electrons and atoms could be labeled with 3 quantum numbers, 3 coordinates that felt like a complete address. First, the principal quantum number, pronounced N. This is the energy level, like the floor of a building. Higher N means higher energy, and, on average, farther from the nucleus. Second, the orbital quantum number, pronounced L. This sets the shape of the orbital, not a planet-like path, but a probability cloud. Spherical for some states, more complex for others. Third, the magnetic quantum number, pronounced M sub L. This tells you how the orbital angular momentum is oriented relative to an external magnetic field. A set of discrete options, not a continuum. With those 3 numbers, the atom looked mapped, elegant, predictable. And then, experiment refused to cooperate. When physicists placed atoms inside magnetic fields and examined their spectral lines, the sharp fingerprints of light, many of those lines split in patterns the theory could not explain. Some splittings were normal, others were not. The so-called anomalous Zeemen effect pointed to something missing, an extra source of angular momentum inside the electron itself. This problem deeply disturbed Wolfgang Pauli. He believed physics should be inevitable, not patched. Around this time, he wrote that physics was confused again, and that he wished he had become a movie comedian instead. But nature was not asking permission. In 1925, 2 young physicists at Leiden University, George Uhlenbeck and Samuel Gaudsmit, proposed a daring idea. The electron carries an intrinsic angular momentum of its own, together with a magnetic moment. They called this property spin. The word sounds harmless, but taken literally, it breaks physics. If you imagine the electron as a tiny charged object physically rotating to produce its magnetic moment, the required surface speed would exceed the speed of light. That is not a violation of relativity by nature. It is a sign that the classical picture itself is wrong. Spin is real, but it is not mechanical rotation. The idea was so radical that the authors reportedly tried to withdraw their paper. They begged their advisor, Paul Ehrenfest, to stop it. He refused, and told them they were young enough to afford a stupidity. The paper was published. Now consider one of the strangest experiments ever performed. In 1922, Otto Stern and Walther Gerlach sent a beam of silver atoms through a strongly non-uniform magnetic field. Classically, if each atom's magnetic moment could point in any direction, the beam should spread into a continuous blur. It did not. Instead, the beam split cleanly into 2 distinct spots. No smear, no middle ground. At the time, this was understood as spatial quantization. Only later did physicists realize that, for silver atoms, the effect directly reveals the intrinsic magnetic moment of an unpaired electron, what we now call electron spin. This result changed everything. Spin is not something the electron does, it is something the electron is. For an electron, the spin quantum number is 1/2, spoken as spin 1/2. When you measure the component of spin along any chosen axis, you only ever obtain 2 results, +1/2 or -1/2. Spoken clearly, +1/2 and -1/2. No intermediate values, no gradual rotation, just 2 outcomes. And now comes the reason this matters. Once spin was accepted, Pauli used it to formulate his most famous rule, the Pauli exclusion principle. It states that no 2 electrons in an atom can share the same complete quantum state. In other words, no 2 electrons can have the same combination of principal quantum number, orbital quantum number, magnetic quantum number, and spin projection. Because electrons have spin 1/2, they belong to a class of particles called fermions. Fermions refuse to occupy the same state. This is why electrons stack into shells instead of collapsing, why atoms have size, why chemistry exists, why solids are solid. When you press your hand against a wall, you are not truly touching it. You are encountering electromagnetic repulsion and the Pauli exclusion principle. The universe simply does not allow those quantum states to overlap. Without this rule, matter as we know it would not exist. Then, in 1928, Paul Dirac entered the story. Dirac wanted a theory of the electron consistent with special relativity. He wrote down what we now call the Dirac equation. And something extraordinary happened. Spin was not added. Spin emerged automatically. A relativistic quantum electron is mathematically required to behave as a spin 1/2 particle. Spin was not a patch. It was a necessity built into space-time itself. Dirac's mathematics revealed something even stranger. In ordinary space, rotating an object by 360 degrees returns it to its original state. But for spin 1/2 particles, that is not true. A rotation of 360 degrees changes the sign of the wave function. Only after 720 degrees, 2 full rotations, does the quantum state return exactly to itself. This is not a metaphor. It is a property of objects described by spinners. Our everyday intuition evolved in a world where this never matters. But the particles that make up your body obey a deeper geometry. So did spin break physics? It broke classical intuition. It ended the idea of atoms as tiny mechanical systems. And it forced physics to accept that mathematics, not imagery, is sometimes the only honest language. Spin cannot be visualized, but without it, the universe would have no structure. The next time you lift a glass of water or feel the floor beneath your feet, remember this. You are being held together by a quantum number that once looked like a mistake and turned out to be one of the deepest truths we have ever discovered. Physics did not break. It grew up. If a single hidden property of an electron can decide whether matter exists at all, imagine how many other truths are still buried in the equations we haven't fully understood yet. If you want to keep exploring the ideas where physics stops being intuitive and starts being real, like this video, subscribe to the channel as we keep uncovering the numbers that quietly run the universe. Veil origins. Impossible truths.